Okay, hope everybody had a good 3-day weekend. It's going to be a short week. In fact, next Friday is the end of the 6 weeks, so we only have a few grades left. The one homework we just turned in, on Thursday, you have your second exam, and it is going to be all over just solving trig equations. Majority of it is multiple choice. I think I put 2 or 3 on there that are open-ended, just like your quiz, so Andrea's really happy about that. Then you got focus activities we'll turn in next week. I've got number 3 I'll give you tomorrow, and it's probably going to be Monday that I give you number 4. Brandon. Okay, then for tomorrow, if you want, let me know before you leave. I'll get you the focus activity, or I can just put one aside, and we're just going to continue these notes. We're finally starting a new unit. We're still going to have a little bit of trig in it, but it's more from a formula point of view. We're going to look at a different topic called vectors. Lexi?
After the lesson, can you write me a pass for tutoring?
Yes, in the morning. Sure will. Just remind me about that. And then, I was talking to Marcus about this in the hallway before class started. We're almost done with the 5th 6 weeks. I mean, things are going to start moving a lot faster. You guys are going to have shorter weeks. In fact, next week we're going to be losing another day because we have to take the district assessment. Unfortunately, it's not optional this time around, so which makes no sense why one is and one isn't. But also, what's happening the week after next? What starts? The 6 6 weeks, but STAR testing. So there's going to be, if you're a senior and you've passed all your STAR exams, then you won't be coming in until like 1:15. I thought it was 1:15. 1:15 or 1:30? 1:30?
It's 1:30.
Okay.
They want you to be there at 1:15 so you can grab lunch
There you go. Okay. But we're going to be losing days because of that. So lots going to be happening. Genevieve? If you're done with your tests and you don't have to take one, then you won't show up until the afternoon. Well, now, the week after next is the English test, English 1 and English 2. And then it's the first week in May, the week of the 6th, that they're doing Algebra 1, Biology, Social Studies. All done? Yes, please. Right over there on the tray. Okay. So a lot of stuff's going to be happening. Really, we're only a handful of weeks away from watching the seniors go across the stage. So I was talking to, again, Marcus. Can we watch Forrest Gump? That's a good movie. Hey, we'll see. I mean, if it, during that last week, if we're done with everything, we would have to just kind of close the deal here. Now, that I don't think would be appropriate.
You heard worse from this class.
True, heard worse, but there's a difference between, an administrator walking in and seeing Miko, I'd be like, oh, damn, I don't have a job anymore. But, oh, yeah, that'll solve it. There you go. That'll make it better. He walks in, where's Mr. West? So not only did he leave the classroom, he put on Blood In, Blood Out.
No, that's Blood In, Blood Out while he went to go.
There you go. Okay. Okay, well, let's go ahead and get started on our next set of notes today. We're talking vectors and a little bit of information. It says the physical world is filled with applications of vectors. For example, your speedometer represents how fast you're driving. This value is known as a scalar because speed can be defined by its magnitude only. Only the value or number is important. Temperature, area, mass, time, they're also examples of scalar quantities. They're things that are measurable, but they're not classified as a vector because you're missing one key part. Now, when we're concerned with both direction and magnitude, such as velocity, then we have a quantity called a vector. So it's 2 key components. Like, for example, speed is a scalar, because it's something that's measurable. You can look on your dash and see how fast you're moving in your vehicle, but it only becomes a vector if you have a direction. So speed and direction. And it's not just speed, in here, a lot of times we might be talking about length, okay, the actual distance between 2 items. We could be talking about force. We'll be talking about a little bit of physics in here, not a whole lot, because this is not a physics class, but just some of the ideas that we could be seeing when we're looking at vectors. So vector applications appear in economics with the velocity of money, vector graphics and computer graphics, and probability vectors and statistics. Okay, so a directed line segment is a geometric representation of a vector. So basically that's what a vector is. It's an arrow, okay, that has both magnitude and direction. So the direction is the easy part. That's going to be used in the coordinate grid and just talking about, whatever degrees you may have. Now the magnitude, like I said, could be anything. Typically for us in here, it'll revolve around probably the speed of an object, the distance between two objects, or the force applied to an object. All right. The starting or initial point P is called the tail or base, and the terminal point Q, indicated by the arrow, is called the head or tip. So we always have 2 points on a vector. We have the initial. This is where you start, and then we have the terminal. This is where you end up. The magnitude or length of V is denoted as this. So there's going to be a lot of notation in here because we're going to have some formulas. So every time you see absolute value, but it has double bars, that's going to refer to the magnitude. Okay. So without actually having to say, find me the magnitude of this vector, I could just give you that notation. Okay, and we'll talk about what that means in just a second. In most textbooks, vectors are represented by boldface lowercase letters like U, V, W, A, B. Typically, these are the most commonplace ones that we're going to have. Pretty much vectors U and V, we'll be seeing those a lot. Okay, so 2 non-zero vectors, U and V, are parallel if the lines through the vectors are parallel. Parallel vectors can point in the same direction or opposite directions. Okay, a vector that is moved parallel to itself without changing its length or direction is a translation. A translated vector has the same magnitude and direction, but different base points. Translated vectors are said to be equivalent, and we'll start looking at more of these when we get to an example. Right now, this is more just the information at the beginning. Now, a vector with its initial point at the origin is said to be in standard position. This is what we like to do with vectors a lot. We love to start them at the origin because it's really, really simple to work with vectors there. Okay, every vector can be translated so that its tail is at the origin. Every single one of them. Okay, now you don't have this in your notes, but this should just kind of give you an idea of the difference between what we would call a scalar, an item that is just measurable, or a vector, something that has both magnitude and direction. So let's look at the first one. Is it a scalar or a vector? A boat traveling 15 miles per hour. It's very good. We have speed, but we don't have what? We need a direction for the boat to be going in order to be called a vector. So this is a scalar. What about a hiker walking 25 paces due west? This is a vector. Now here, the magnitude is the distance that he's walking, but more importantly, we're given a direction. That's a vector. Okay. What about this one? A person's weight on a bathroom scale. Oh, now this one's tricky. This is actually a vector because there's a force, a pull of what? A pull of gravity. So it's actually pulling us straight down. Okay. So acceleration due to gravity is a vector. Okay, we're just being pulled straight down, so we actually do have a direction. Yeah, that one's a little tricky. A car traveling 60 miles per hour, 15 degrees east of south. That's a vector because we not only have speed, but we have a direction. So that's a vector. What about a parachutist falling straight down at 12.5 miles per hour? That's a vector. Just like standing on the bathroom scale, he's going what direction? Straight down. So that's a vector. What about a child pulling a sled with a force of 40 newtons? That's a scalar. See, we have magnitude, we have the force, but we don't have a direction that that force is going. So that's just a scalar. Okay. Does that kind of help to make sense of it? So a scalar is something that's measurable, but a vector has both force, or excuse me, magnitude and direction. Has to have both. Okay. Now the term scalar is another word for real number. The product of a vector v and a scalar k is the vector that is k times as long as v. When the scalar is positive, the product kv has the same direction. However, if it's negative, then it's going to go in the exact opposite direction. So we're going to do some of these graphically, but we're going to depend more on these algebraically. But let's start with the graphical. Given vector v, so this is vector v right here. Sketch each scalar using the grid at right to represent each new vector. So we have a direction that he's pointing, and we know his length. Let's say it's 2 units right here. So what vector would result if I wanted to take 2 times vector v? It would have the exact same what? Direction or length? It would have the same direction, but which one would change? The length. So I want twice what this vector is. So let's see if I can draw it any accurate. So it would be twice as long, but going in the exact same direction. Okay. Now what about negative 2v? It would change in the exact opposite direction. So if you're going one direction, then it's 180 degrees in the exact opposite. But what about the length? See, it's still twice the length. The negative just changes the direction. So it'd probably look something like this. Okay. What about 3/2 v? Now, would the direction change? Oh, no, we're always comparing it to the original. Okay. Just the length. So the direction stays the same. What's the decimal value of 3/2? 1.5. So see, I wanted 1 and then just half of the length that we have. So it would take 3 of these. And see, it doesn't matter if I go ahead and draw it right there or if I were to start it down here. Okay, it's still got the exact same length, the magnitude, and the direction remains the same. Yes, that's all you need. That's exactly right. What about negative 1/2 v? So change direction and the length. So I only want him half of what he originally was. But now it's going in the exact opposite direction. That's what a negative will do. It will change the exact direction of a vector. Okay. So how are we doing so far? Not bad? Okay. Well, let's see what else we got. Component form of a vector. Okay. If v is a vector in the plane whose initial point is the origin and whose terminal point is AB, then the component form of v is given by this. Now, this is something we're going to see over and over again. It looks like an ordered pair, and it's going to act just like an ordered pair as well. But the reason we know we're dealing with a vector, instead of the parentheses, you have those arrows on either end. This is what we call component form. This is directions, how to move horizontally from an initial point to the tail point, or excuse me, to the terminal point, horizontally and vertically. Instead of using X and Y, they're just using A and B. So A moves you left and right, B moves you up or down, depending on where it is. And that makes sense because if you have, a coordinate plane here, if you're starting at the origin, A, you'd go left or right, and then B, you'd go up or down from that. They just I'm not sure why, but when we're dealing with vectors, instead of X and Y, they prefer to use A and B. Okay, but it doesn't change their relationship. Okay, now the magnitude of a vector. If point P, x1, y1, and Q, x2, y2, are the initial and the terminal points. So the first one given will be the initial. The second one given is the terminal. Okay, for a vector PQ, then by the distance formula, it can be shown that the magnitude of V is, now you can go ahead and use the distance formula, but this is what we like to use. You remember before I said if it shows double bars, okay, if it looks like absolute value, but there's a double set of bars, that's the magnitude. So really, this is just the square root of a squared plus b squared. The square root of the first term plus the square root of the second term. That's what we're going to be doing. Now, a few other things, because it went ahead and brought this up. We can use certain lowercase bolded letters to represent a vector, but there's other ways to do it. Think about geometry. If I were to go ahead and say AB, whatever I wrote above would indicate to you what it was. So like, for example, if I did that, you'd recognize AB as a what? A line. Okay, so that would be line AB. If I did this with no arrows, then it's not a line, it's a segment. So it starts and ends someplace, right? Well, vectors, if you want to use the initial and the terminal points, you can do the same, but it looks like an arrow going in one direction, but for a vector, it only has the top part of the arrow. That's a notation to let you know that you're dealing with a vector. And you can also use those with the lowercase letters as well. Like if we're going to say vector u, you could put that little arrow, but just with not the bottom half. That's another notation to let you know we're dealing with a vector. Is everybody okay with that? Okay. Yes. So you could either use the points of the initial and the terminal, or just whatever you're calling the vector with that symbol. Or if you just wanted to say vector u, you could actually say vector and then u, whatever you like. Okay. So let's see here. Given vector v, okay, AB, so A is the initial point, B is the terminal, write the component form of vector AB. So this is something you'll be doing quite often. So here's the thing. Let's say we have A is 3, 7. So 3, 7 would be right here. So there's A. And then B is 6, 5. 6, 5. Okay, so here's A, here's B. So here's this vector AB. And I know I'm going to put the terminal end at B because he's the second part. It always goes in order. The first point is where you start, the initial. The second point is where you finish. That's the terminal. Okay. Well, let's go ahead and figure out what the component form is. It's really easy to do. All you want to do is take the difference of the x's and then the difference of the y's. But there's one thing. Always, always, always start with the terminal and subtract the initial. If you want to find component form and you've got the two coordinates, always, always, always start with the terminal. Okay? So here's the initial. Here's the terminal. So I'm going to start with the x's. So the terminal x is 6. What am I going to subtract from it? 3. And now I'm going to do the same thing for the y values. So the terminal y is 5. What am I going to subtract from it? Okay. So what is 6 minus 3? 3. And then 5 minus 7? -2. See, there's your A, there's your B. Component form, it's a set of instructions that tells you how to get from your initial point to the terminal. Okay. Remember, A, we go left or right. So how would I know if I go left? The value would be what? It would be negative. See, it's positive, so I would go right. What direction do you think I'm going to go for B? Up or down?
Down.
Why down? It's negative. So take a look here. Going from point A to point B, right here. So didn't I go 3 to the right and then 2 down? That's what component form is. It always tells you horizontally and vertically how to go from the initial to the terminal. Okay. Well, now it says find the magnitude of AB. So here the magnitude is the length. So I want to know how long is that arrow. Well, that's the formula that I was just showing you. So the magnitude, I'm going to put the double bars here. It's the square root of a squared plus b squared. Okay. Well, the square root. What is a? A is 3. That's always the first value. So 3 squared. Plus b squared. What's b? -2. And let's see. 3 squared is 9. -2 squared, 4. So 9 plus 4 will give me 13. There you go. That's the magnitude. That's it right there. And you'll notice the one thing you're always going to be able to do with the component form, because you're moving horizontally and vertically, those are going to create the sides of a right triangle. So if I were to use the Pythagorean theorem, I would also end up with the square root of 13. That's what the formula is. It's just the last step of the Pythagorean theorem. And then it says, sketch the vector AB and the translated vector V. So this right now, this vector is not in standard form. What do they call standard form? When the initial point is where? At the origin. So if I were to slide this vector so that A touches the origin. Okay. Now remember, we wanted to go 3 to the right and 2 down to get to the terminal B. So there you go. Now it's in standard position. Putting the initial on the origin, that's standard position. Okay. How we doing? Okay. So let me go ahead and give you another one, another example just for practice. Let's say I had, let me go ahead and erase this. Let's say I have an initial point A. Okay. Let's say -1, 6. And I've got a terminal point B is equal to, let's say 7, 3. Okay. Now this is just an extra example. You can follow along. You don't have to graph it or anything. But let's say I have these 2 points, and I want to know what's my component form. Okay. So we always take the terminal and we subtract the initial. Okay. So the component form. Now, which one here is the terminal? Which one's the initial? -1, 6 is what? Oh. Oh, no. Each point represents one of them. So 2 points. 1 point is initial. 1 point is terminal. So which one's A? Yes, but is it the initial or the terminal? That's part of it, but this whole point, that's the initial. So that means point B is your what? Terminal. And I mean, without being directly told that, how would we know? The what? The order. The one that comes first is the initial because that's where you start. The point that comes last, that's the terminal. Okay? So if I want component form, I'm going to subtract the x's. So 7 minus -1, comma. Remember, I always go from the terminal to the initial. So I'm going to take 3, what? Minus 6. So I subtracted those. And you'll notice I'm putting those arrows at either end to indicate this is a vector. Okay. Well, what happens when you subtract a negative? It's positive. So that 7 plus 1 would give me 8. And then 3 minus 6. -3. Okay. Remember, this component form is instructions on how to go from the initial to the terminal. So let's see if that actually worked out. If I were to plot these, -1, 6. -1, 6, that's my A. That's the initial. B was 7, 3. Okay. So this right here. All right. So let's see. Remember, you move horizontally and then you move vertically. So because this is a +8, am I going left or right? Right. So let's see. From here, 1, 2, 3, 4, 5, 6, 7, 8. And that lines up with B. And then how far down would I need to go? 1, 2, 3. See, that's what component form does. It tells you horizontally and vertically how to go from the initial to the terminal. Component form is always made up of the 2 variables. The first one is A, and this one's B. Now, let's say I wanted the magnitude of that. I wanted to know the actual length of the vector. Okay, so the formula, the magnitude of vector AB, it was the square root of A squared plus B squared. Okay, well, A is 8, so what's 8 squared? 64 plus 9, -3 squared, is equal to the square root of, what's 64 plus 9? 73. So the length of that vector would be the square root of 73 units long. Okay, any questions about component form? And here's also something really nice. If you have a picture of it, you don't even have to go ahead and tell me or show me the work here. Like, let's say we have a vector that starts here and stops right there. Let's call this U. And I want to know what's the component form of U. Well, I want to go from the initial to the terminal. So horizontally, would I have to go left or right first?
Left.
Left. So the answer would be negative. In fact, negative what? So negative 2, and then positive or negative? Positive, because from here I'd now have to go 1, 2, 3, 4, 5, 6, 7. So see, that vector would have a component form of negative 2, 7. Horizontally and vertically moving from one end to the other. Yes, ma'am. It depends on what you're given. If you're given the graph, you could probably just immediately tell what it is. But sometimes they might not give you the graph. They'll do like we did here. They'll give you the 2 points, and then you have to find component form and then go from there. Okay. Okay, so questions. Okay. So let's see here. Let me go ahead. Let's try some examples. All right. Now this is not on your paper, and that's okay. Let's say this is vector u, v, and w. Okay. Now where the arrow is, that's the terminal side. Remember, that's where it finishes. So just by looking at these, I want you guys to be able to tell me what the component form is going to be. So what do you think it would be for u? So I want to start here. How far right did I have to go? 7? So it looks like I went and had 6 right. And then what? Up 3? Up 2. So the component form for u should be 6, 2. So I went 1, 2, 3, 4, 5, 6 to the right. And then I went 2 up. That's what component form is. Horizontally and vertically, how I go from the initial to the terminal. Okay, now let's do V. Okay, so I want to go from this point at the origin to this point right here. So negative 2, because I got to go left. 1, 2, 3, 4. So the component form for V, whoop, if I didn't drop this, should be negative 2, negative 4. See, it works just like an ordered pair, but we know it's a vector because of those arrows. Now here's one that's interesting. What do you think about vector W? What would his component form be?
0, 0.
Now 0, 0 would just be a point.
0, 5.
Oh, you're close, not 0, 5.
5, 0.
There you go. Because see, I want to go from this point here at the origin to this point right here. And I got to move horizontally first. So 1, 2, 3, 4, 5. But then I did not move up or down. So that would be 0.
So there would never be a case where 1 is 5. Unless.
No, actually, yeah, you should be able to go from one to the other. So if it is vertical or horizontal, one of your distances is just 0. So like what you said, 0, 5, that would actually be this vector right here. See, I did not go left or right, but I went up 5. Okay. Is anybody having trouble with component form? Any questions on that? And component form is actually really, really useful to us. Okay, so I'll tell you what, I will go ahead and stop there for today. We've covered enough information.